Welcome to this lecture series in real analysis. In this lecture, we'll discuss monotone sequences and look at a certain theorem which is very important. The theorem says that every bounded sequence of real numbers has a convergent subsequence. So that's very interesting. And let us recall roughly what we need to follow this lecture. So, of course, we will need to know what is a convergent sequence. We have discussed this so many times that there is no point going into the formal definition again here. Perhaps we don't need, but let me anyway recall that every convergent sequence is a bounded sequence. Okay? And we will need the algebra of convergence. By that I mean the following facts, that if we have, suppose, two sequences xn and yn with both of them convergent and their limits being x and y respectively, then we have the limit of the summed sequence is the sum of the limits, and the limit of product is the product of limits. And we did a scaling version, but the scaling version is a special case of this one. And we also did one about inverses. So let me not recall that because I don't think I will be using it. Okay, so let's start. Here are some problems for practice. The fourth one here is marked with star, not because it is hard, but because I'm going to use it. It's a very simple problem, but pretty interesting. So let us now begin the lecture. So what is a monotone sequence? First, we will define an increasing sequence. A sequence xn in R is called an increasing sequence if, first let's see what is the idea. So I have drawn some diagram here which is supposed to represent a sequence. So recall that if you have a sequence, you can draw a graph of it. So for n equals 1, you just plot the value of x1. For n equals 2, you plot x2, and for a general n, you plot xn. So you may join them with some lines just for better visualization, but these points are exactly what captures all the values that the sequence takes. Okay, so in this graphical representation of a sequence, you can see that once you assume a value, you never assume a value smaller than it. So here we have assumed a value, some value. All the future values are not smaller than it. They are at least as much as it. The increment may not happen. For instance, from here to there is no increment. But when we say the sequence is increasing, it just means that there is no decrement. There is no strict decrement anywhere. So I hope the idea behind this concept is clear, but formally it's very easy to define. So you say that a sequence xn of real numbers is increasing if whenever m is less than equal to n, we have xm is less than equal to xn. Very simple definition. It captures exactly what we said in this picture. Similarly, you can define a decreasing sequence for yourself. So let me just write down the phraseology. All right, so we have these two definitions, increasing sequence and decreasing sequence. And the sequence is called monotone. Sequence of real numbers, I mean. A sequence is called monotone if it is either increasing or decreasing. Right? So if you have an increasing sequence, we call it a monotone sequence. If you have a decreasing sequence, we also call it a monotone sequence. So there are two kinds of monotone sequences, decreasing ones and increasing ones. Similarly, you can define a strict increasing sequence or strictly increasing sequence. So let me not write it down, but let me say it in words. Strictly increasing sequence is a phraseology. So you say that a sequence xn in R is strictly increasing if whenever m is strictly less than n, we have xm strictly less than xn. That's all. So here what we have drawn is not a strictly increasing sequence because it takes the same value at multiple points. And similarly, you can define a strictly decreasing sequence and a strictly monotone sequence. So let me not do that. You can write it down in your notes. And let us see some examples. So here are our favorite examples. There is an artifact on the screen for some reason. Yeah, no, it's gone. So this is our favorite example. Whoa, I've switched the diagrams, unfortunately. Just give me a second. Yeah. So in this so this is a sequence. Xn given by this is a sequence. We saw this in a previous lecture. This is how its diagram looks like. I mean, the graphical representation of this sequence. I don't know why I have written an F over there. So this the graphical representation of this sequence is just, -1 on odd integers, odd natural numbers, and +1 on even natural numbers. So it is zigzag. And this is neither increasing nor decreasing, and this is not a monotone sequence. So this is not monotone. However, if you take this example, xn is 1 by n, then you see this kind of, the diagram looks like this. You can easily show this is a monotone sequence by, a decreasing sequence, in fact, just by looking at the definition. But graphically, it does look like a decreasing sequence. It constantly falls down. So you have two examples. One is not monotone, the other is monotone. In fact, a decreasing sequence. Okay, so these are very easy concepts, and therefore I do not want to spend too much time on the definitions. But here is the most important thing. This is a very, very crucial ingredient in everything that we are going to do in this lecture. So what we are going to show is that every sequence of real numbers, no boundedness, nothing is required. Every sequence of real numbers has a monotone subsequence. Right? You pick a sequence of real numbers, it will have a subsequence which will be monotone, either increasing or decreasing. Very interesting fact. In fact, I encourage you to think about this before looking at the proof. So yeah, let's try to prove this. Okay, so fix some arbitrary sequence of real numbers. Okay, and we want to show that there is a subsequence of it which is monotone. So here is the main concept that we will use. So we say that a natural number n is a peak. Let me use a different color. Is a peak if this happens. So xn dominates, or maybe I should say, okay, give me 1 second. Let's write it like this. Yeah. So you have this time n. So at time n, suppose this is the integer, and the sequence has some value, xn is some real number. We say it is a peak if beyond the time n, always you see the value of the sequence is at most that much. So you do not see anything above it beyond this point. So that's the meaning of a peak. Okay. Now there are two cases. Case 1. Case 1 is that there are infinitely many peaks. So there are two cases. One is that there are infinitely many peaks, and the other is that there are only finitely many peaks. Of course, only two cases are possible. So in this case, say n1, n2, ... are all the peaks. Right? If there are infinitely many peaks, you should be able to find an increasing sequence of natural numbers such that all of them are peaks. But now, since these are peaks, since n1 is a peak, we have x n1 dominates xk for each k coming after n1, and therefore in particular it dominates x n2 immediately from the definition of a peak. By the same reasoning, x n2 dominates x n3, and this goes on. And what we have found is that this subsequence is monotonically decreasing. It's a decreasing sequence and hence monotone. Case 2 is that there are only finitely many peaks. Okay? So in this case, what we will do is we will end up producing a subsequence which is monotonically increasing. Alright, so since there are only finitely many peaks, there is some natural number, capital N, such that n is not a peak whenever little n is at least capital N. Right? Since there are only finitely many peaks, after a certain point, there will be no more peaks. And let's say that point is capital N. So whenever the time is capital N or more, n is not a peak. Okay, so in particular, therefore, let's define. So therefore, n1 defined as capital N is not a peak. And since it is not a peak, there is some k exceeding n where this fails. Right? There is some k exceeding n for which this fails. Maybe I said it the reverse way. So since n1 is not a peak, there is some k exceeding n1 such that xn1 fails to be dominating xk. So what I'm saying is, so n1 is not a peak, and hence there is n2 strictly greater than n1 such that this must happen. There exists such an n2, because if there were no such n2, n1 would become a peak, but n1 is not a peak. Now, since n2 is greater than n1, n2 is also not a peak, because n2 also comes after capital N. So n2 is not a peak, and therefore there is n3 such that this happens. And you can continue. You can find n4, n5, n6, and these inequalities will show you that you have in fact, a strictly increasing sequence. Okay. So this finishes the proof of this particular theorem, a very important theorem. And let us continue. So now we will show an independent fact, independent of the previous proposition, that every bounded monotone sequence is a convergent sequence. And this should be intuitively obvious. Suppose we have a bounded monotone sequence. So first of all, its graphical representation will look something like this, but there is a ceiling which it cannot cross because it is a bounded sequence. There is some ceiling which it cannot cross. So ultimately, it should approach a certain ceiling. That is roughly the idea. And the ceiling that it will approach is the supremum of all these values. So all of this should be very, very believable, but we have to properly prove it, formally establish this. So let's do it now. Okay, so start with a monotone sequence and we will prove it for monotonically increasing sequences. A similar proof will go for monotonically decreasing sequences. So in this picture, we had an increasing sequence, and therefore we will take the supremum of the sequence, and that will be what the sequence will converge to. If it were a decreasing sequence, we would have taken the infimum, and that would be what the sequence converges to. All right, so let xn be an increasing sequence. Okay, which is bounded. We want to show that it is a convergent sequence, and to that end, we define x as the supremum of all the values that the sequence takes. Right? This is what we explained in this picture. The best possible ceiling, the most economical ceiling is x. Okay, so we claim that, or we will show that. Right, this will finish the proof. So to show convergence, we fix an epsilon. Fix an epsilon greater than 0 arbitrarily. Okay. Suffices to show that, and note this point, suffices to show that suffices to show this much, because as soon as you show this, automatically it implies this, because this is a positive quantity. X is the supremum of all the xn's, and this is anyway positive. So as soon as you show this, you have already shown that it actually happens in the absolute value, which is the definition of convergence. Okay, so maybe I should have stressed on a certain point. Since the sequence is bounded, this x is a real number. It is not infinity. So this is why we are able to take this difference and all. Okay, so this is the final thing that we need to do, the orange thing. Okay, but further observe that it is enough to show that. Further, it suffices to show that for some n. Here we wanted this to happen ultimately, which means for all n beyond a certain point. But here we are saying that it is enough to show that this happens only for just for one single n. As soon as this happens for one single n, it will happen ultimately. And that is because this sequence xn is an increasing sequence. So if this is less than epsilon, as soon as you increase the value of n, it will continue to be less than epsilon, because the value of xn will increase as you increase n. So this much is sufficient. Okay. And to now finish the proof, assume on the contrary that the blue thing does not hold. That x minus xn is at least epsilon for all n. At least epsilon for all n. Then x will be greater than equal to epsilon plus xn for all n, which implies x exceeds the supremum of this set I shouldn't say exceeds, I should say at least. X is at least the supremum of the set. Right? X is an upper bound and this is the least upper bound. So any upper bound should dominate the least upper bound. That is the argument why this is at least that. Okay, we have that, but you should be able to see, I'm sure at some point this must have been an exercise, that this entity is actually epsilon plus the supremum, which implies x is at least epsilon plus x, and that is a contradiction. Contradiction to basic thing about numbers. Contradiction, and therefore we are done. So we have shown that this blue thing must hold, and hence this orange thing must hold, and therefore the pink thing happens, and we are done. Okay, finally we will prove what is called the Bolzano-Weierstrass theorem. Oh, before that we have an example. So it's important to look at examples. Sorry about that. So fix some a naught in this interval. So when I write this, I just mean that this just means that a naught is strictly between 0 and 1. So we are given this, and now we define a sequence, and this sequence starts with 0 as follows. The n plus 1th entry of the sequence is 1 minus this thing of the nth entry of the sequence. This is for all n at least, this is for all n at least 0 in fact. Okay. So what is a1? a1 is 1 minus square root of 1 minus a0, right? You substitute n equals 0, you will get a1 is equal to 1 minus square root of 1 minus a0. If you substitute n equals 1, you get a2 equals 1 minus a1. So this is kind of the seed which generates an entire sequence in this fashion, and you may want to fire up your Python or C or whatever programming language and may want to plot this. It's fun to play with such things. But what we want to show is that an converges to 0 as n approaches infinity, which just means that this is a convergent sequence and in fact a null sequence. So we want to show that this is a null sequence. Okay. So first of all, yeah, so I mean, you're encouraged to pause the video and solve it yourself, but let me give a solution. So note that first of all, that this is a sequence of strictly positive numbers, right? An is 0 greater than 0 for all n. How do you show this? You show this via induction. Once you have this is strictly positive, and in fact I should say not just strictly positive, but it is also strictly between 1 and 0. So why? Because once you establish that an is satisfying this, then an plus 1 automatically satisfies this also, because this number is strictly between 0 and 1, and hence this number is strictly between 0 and 1. So once an satisfies this condition, an plus 1 also satisfies this condition, and the base case of the induction is that a0 satisfies this condition. So this is true for all n, and you're encouraged to fill the details if this is not immediately clear. So we have this, or maybe it's better to write it in the other way. This looks better. Okay, we have this. And now the main observation is that observe, or rather maybe consider, or maybe just say we have that an upon an plus 1, by definition this is an upon this thing, but now you multiply above and below by this number, right? It is legitimate to do this because this is a non-zero thing, and of course an plus 1 is non-zero, so it is legitimate to consider this ratio to begin with. So we have this is equal to that thing, but 1 minus something times 1 plus something, you just do your high school thing. So this becomes an times this quantity, and the denominator is actually an. So this times that is an, just note that. And here I should have put a bracket. So this an cancels off, and we end up with 1 plus this expression, which is strictly greater than 1. And therefore, what we have shown is that an divided by an plus 1 is strictly greater than 1 for all n. I can write n greater than equal to 0, which implies an is greater than an plus 1 for all n. So the upshot is that this is a decreasing sequence. This is a decreasing sequence. I need more space, so let me push things a little bit. So the upshot is that an is a decreasing sequence. Let me just say monotone. In fact, it's a bounded monotone sequence. Why is it bounded? Because of this condition. And it is monotone because of our argument. So it is a bounded monotone sequence, and hence this converges. So say A is the limit of this sequence. It converges to something. A is the limit. And therefore, now this is the interesting part, or maybe I will break it down into steps. So this implies that 1 minus A is the limit of this thing, right? So we are doing our algebra of sequences. You have a difference of two sequences. The first one is a constant sequence 1. The other is your an, or you can think of it as the sum of the constant sequence 1 and minus an. And it is easy to see that the limit of this will be 1 minus a. So it is just the algebra of sequences that we recalled. So we have that. And now by the star marked problem, we have this is the case, right? Because all of these are non-negative real numbers converging to something, and therefore their square roots will converge to the square root of the limit. So this is the star marked problem. Okay, and therefore once again we will use algebra of convergence. This implies 1 minus this expression is the limit of one minus the thing inside. Right? This is an immediate consequence of this. Once you have this, you get that. But what is this? Since I do not have space, I will just scratch it out here. This is an plus 1. This is an plus 1. This is an plus 1. But what is that? And now here is a small thing. It's a very, very basic thing. Suppose what you have is limit of some sequence is x. Then you also have the limit of the shifted sequence, if you will, is also x. It's a very, very obvious and trivial fact. If beyond a certain n, all the entries hover around little x, then all the entries here also hover around little x beyond a certain point. That's the t-shirt version of the argument. You can write down a formal argument. Perhaps I should have given this as a problem. But just using that fact, we have this limit is same as this limit, which is a, by definition that is a. And now just look at this equation. A is a non-negative real number because it is a limit of non-negative real numbers. A is a non-negative real number satisfying this equation, and hence necessarily A is 0. So that's the proof. This shows that this goes to 0. We have shown that A is 0, and that is what we wanted to do. Okay, so It is important to follow all these steps here so that the material we are learning gets absorbed. Alright, so finally we can finish the lecture with Bolzano-Weierstrass theorem that every bounded sequence of real numbers has a convergent subsequence. We have collected all the pieces necessary. I'll just say it in words. Start with a bounded sequence in real numbers. We want to produce a convergent subsequence. Now, since the sequence is bounded, it has a monotone subsequence. We proved this. So we started with a bounded sequence. We get a monotone subsequence. Monotone subsequence. But any bounded monotone sequence converges, and since you start with a bounded sequence, the monotone subsequence you will extract will also be bounded, because every subsequence of a bounded sequence is bounded. So starting with a bounded sequence, we get a bounded monotone subsequence and hence a convergent subsequence, because every bounded monotone sequence is convergent. And that is the proof of this fact. So let me not write it down. You can write down in your notes. And this is the Bolzano-Weierstrass theorem. With that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.